Okay, good afternoon, and I would like to thank the organizers for this amazing conference. So, actually, this is a work that was initiated by Alessandro Casalino, David Mota, and Parvot Hassani in Oslo, and recently I joined them, and it's actually an ongoing project. So, yeah, let me start with uh, our current view about the universe, which is based on several assumptions, including homogeneity and isotropy in large scales, which dictates a holodynamic metric. And also, we assume that some inflator error is responsible for the initial conditions of perturbations and also for expansion history because um, Big Bang model is itself a bangless model. It's only about the aftermath of a bang. It doesn't tell us anything about why this bang happened. But with inflation, we can explain that. So the initial conditions come from inflation. We have also two phenomenological components in the matter content. And also, we assume that equations of motion come from general theory of relativity. From early times, when this standard model of cosmology was being established, at least theoreticians were not happy with this much phenomenological contents for dark sector, and they were seeking for some microphysics or. But observationally speaking, we used to be so happy we could explain and actually predict cosmic microwave background and its anisotropies, we could predict expansion history, and we can measure it right now very well. And things used to be very consistent with our picture, standard picture, maybe a decade ago. This is from Planck 2013, and you can see that WW naught contours are more or less compatible with lambda. But this is not the case anymore, as you all know, and it seems that our standard picture is not compatible with the data anymore, and not only lambda is sort of ruled out if we assume that this sort of actually analysis is valid. Not only lambda is not the case anymore, but also evolution of dark energy is doing something not very pleasant, which is crossing the phantom divide. So nowadays, not only we have theoretical motivations to go beyond lambda, but also we have many observational ones. Besides from this, we have H-Mac tension, I don't know, CMB high and low anomalies, and lots of discrepancies. So, whose blame is it actually? Maybe we should go not a philodynamic cosmology, assuming Bianchi type or Gordon type or whatever, something more complicated, or maybe we should change our notion of initial conditions somehow, or we can just change our assumptions about dark sector, or more or less equivalently our theory of gravity. So how can we actually change this theory of gravity? Thanks to Tessa Baker, we can look at this map of all the alternatives we can have as our theory of gravity, and you can see that we can assume higher dimensions, non-local gravity, higher order terms. And one important subclass is where you introduce a new degree of freedom in addition to original two tensorial modes, which is called scalar tensor theories of gravity. But actually, this subclass itself is so huge, and we can get lost in this hyper space of theories. So people have developed effective field theory of dark energy, in which you just write down every possible operator here. Actually, it goes to infinity, but I have cut it off here up to quadratic order. So we just write down every possible operator which respects three-dimensional diffeomorphism. These green terms are operators. Also, we have some coefficients, these EFT functions, red ones. And instead of examining many theories of scalar tensor theories, we can just confront this action to the data and determine this EFT function. For example, we have seen that dark energy evolution is crossing the phantom divide. So we can ask which operator actually is able to do that. This is something that has been done here in this PRL paper. Jenny, Alessandra, Silvestri, and their colleagues, they have actually tried to reconstruct these functions using DESI, CMB, and other data. And here you can see that, for example, EFT function, gamma 1, 2, or 3, or quintessence, which is not C, these EFT functions are not able to explain this result, okay? But this omega actually is able to do that. So it seems that non-minimal coupling is important. So we are now motivated to explore a non-minimally coupled quintessence, which we call it extended quintessence. In this model, as I told you, there is non-minimal coupling in addition to canonical terms. So we should determine shape of potential and also this f of phi. This is our choice, actually. We have this form of f, and addition of this term, phi to the squared, guarantees that this theory is compatible with all the Cavendish-like experiments, because we know that nowadays M-Planck effective should be 1, right? I mean, this F should be 0, actually. Also, we have assumed some inverse power law for potential. So, for example, here you can see evolution of M-Planck effective at high redshift, depending on the sign of alpha or value of alpha. It is something away from 1, but then it converges to 1 today. So I can say something about the amount of healthiness of our theory. Actually, I can just give you this message that if we have this f such that it's always greater than -1, which means that our effective G or M-Planck squared is never negative, never negative, then our theory is healthy and devoid of any instability. Okay, let's see the background behavior of this model. How can we define effective density and pressure of this non-minimal coupled scalarity? We decided to define it in a way that Friedman's equation retain their original form, which is this, right? This yields these expressions for density and pressure of dark energy. These are familiar ones, but because of non-minimal coupling, we have other terms. And you can see here that if f is not 0, then this term is a fraction of critical density at any moment. And something similar is for pressure. So if, in our case, because f of phi is not 0 at early times, actually these two terms are dominant, and the equation of state of phi at early times can be approximated well with this formula. let me show you the plot. So this is the plot, and as you can see, at early times, this scalar field actually has equation state of 1/3, which effectively is similar to a change in n effective, right? And then when matter is dominant, its equation state becomes 0. And then when the scalar field takes over, it plays its own game and it does whatever it wants, and the Klein-Gordon equation says, actually, you might be a bit concerned about this divergence in W of phi, but actually nothing is diverging. I mean, pressure is not diverging. This is only because rho is crossing 0, actually. Because as you can see here, if the f of phi is positive, then, and also this term is dominant at the universe, then density of phi, effective density of phi is negative. So at some point it should cross 0, so P over 0 diverges, which you can see here, for example. You can just look at the blue line and red line, which are fractional densities for phi for two scenarios, two different values of alpha, minus or plus 4.05. You can see that it is actually negative until some redshift, and then it approaches a good fraction of critical density today. Or for positive alpha, it does similar thing, but it's always positive. Also, I should mention that you can see here that for negative values of alpha, this phantom crossing is happening here at recent universe. So maybe it is interesting in this regard. Another thing that I would like to mention here is if we plot the angular particle spectrum CMB for this theory, for different values of alpha, let's say, you might be able to see, I don't know, but you might be able to see that when we increase alpha, the peaks are moving forward in L space. That means increasing alpha is equal to decreasing the angular scales in the CMB map. Which parameter in standard lambda CDM does that? H0, right? When you increase H0, actually that does the reverse. When you increase H0, you are actually increasing the angular scales on CMB map. So there is a degeneracy between alpha and H0, which we hope that it might reconcile CMB with local measurements of H0. But actually right now we're doing MCMC and we are testing it. So I can actually stop here, and I will I can leave the review page here. Stop here. But let me just say that actually we have derived the perturbation equations up to second order, and we are almost ready to implement it into G-evolution to examine it on smaller scales and perhaps rule it out more precisely. Yeah. Okay, thank you.
Okay, I have a few questions, very simple questions. So you have two more free parameters, sigma and alpha, yes?
Yes, exactly. But you might say that lambda. You might say that lambda is also free, but it's not. It comes from a shooting method because we demand lambda to be such that we have actually 0.7 times critical density today. Yeah.
See, like nowadays I'm using real data, so I'm far away from this. What happened to that phi today? How you fix that in slide number 10?
Yeah, that is actually
determined.
Yeah, this is actually actually this is determined with a shooting method. So we start from an answer, and then we run, and then we just move from another point such that phi in the end equals our answer. I mean, we correct our answer with each iteration. So using a shooting method, we can find phi today.
So you don't put this to vary your answer. So
No. This is determined by shooting method.
Yeah, one more is if anybody else has one.
Okay, I really didn't expect this phantom crossing for quintessence like extended. Is it normal? Like happening?
Yeah, actually, when you have non-minimal coupling, this can happen. That was the whole point of this PRL paper, which is.
And the last slide, I think, besides lambda, besides h0, also curvature can move this. Like this.
Yes, but we assume flatness actually.
But like, yeah, if you have curvature, that can also move your, peaks like this, I think, together with h0. So maybe there is a degeneracy between your curvatures.
In principle, yes.
But you're pretty sure that your curvature is, you don't know.
Or we just fix it. We're not sure about. Yeah, we just fix it to 0. Yeah.
Okay, so let's thank again the speaker.